We are ready now to start talking about applications of exponential functions. But for the time being, I'd like to skip down to where it says continuous compound interest and the number e. The formula for compound interest is amount at time t equals p the principal times the quantity 1 plus interest rate over n, quantity to the nt, where n is the number of times interest is compounded per year. And what we want to do right now is investigate what happens as the number of compounding times per year goes to infinity. And to do that, I want to pick some specific numbers for some of the other variables. So let's let P be 1. So you've invested $1. And let's let R be 100%. In other words, 1. And let's let T be 1 year. So at that point, the amount that we would have after 1 year is the principal 1 times 1 plus 1 over n to the n times 1. In other words, the amount we'll have after 1 year is 1 plus 1 over n to the n power. Now, I know this is a silly example in a way, because who would invest just $1 and there's no way you're going to get 100% interest? But let's just go with this for right now because it simplifies the mathematics. And again, we're asking ourselves, what happens as the number of compounding times per year goes to infinity? I'm hoping this will look somewhat familiar to you, because remember we said that if you take the limit as n goes to infinity of 1 plus 1 over n to the n, you get e. This is one of the reasons e is an important number. I mean, e is totally magical. You'll be doing some kind of mathematics and you work through it and boom, e pops out like magic. Dan, I don't want to burden you with all those ways that a person can run into e. For this class, this is the most important way. It has to do with compound interest. And if you keep compounding oftener and oftener and oftener and oftener, it'll turn into being like e. And how that turns into continuous compound interest is really beyond the scope of this class. But here's the formula, and I'll give you my take on it. The amount at time t, if you're compounding continuously, is the principal invested times e to the r. R is the annual interest rate, and then t is the number of years. Maybe we should get that in the notes. A equals amount after t years. P is the principal. I'm not going to write this out, but hopefully you know that means the amount invested originally. R is the annual interest rate. expressed as a percent, as a decimal, and t is the number of years. So here's my take on what's going on here. Let's get all medieval and think of you investing some gold coins in a savings account. And if it's been compounded yearly, so you're getting interest once a year, that means clunk, there's a blob of gold coins that goes in at the end of the year. If instead it's being compounded quarterly, then every 3 months, clunk, a few gold coins, clunk, a few gold coins, clunk, a few gold coins. If it's being compounded daily, clunk, 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 every day a few gold coins drop in. If we're thinking about compounding continuously, we're thinking not just compounding daily, but compounding every hour. But not just that, compounding every minute. But not just that, compounding every second. But not just that, compounding every tenth of a second, every hundredth of a second, every billionth of a second. It ends up being like if that interest that you're getting in your gold coins, if they melted the gold coins and just gradually, continuously poured it in. That's what continuous compound interest is, and that's what this formula expresses. For example, how much money will have accumulated after 15 years, given an initial investment of $2,000, earning 8% annual interest, compounded continuously? And by the way, I've used some of the same numbers from an example a little higher up on the page. Anyway, since it tells us that it's compounded continuously, that tells me that I'm going to be using the formula amount at time t is p e to the rt. The question is, how much will we have after 15 years? So I put in P, the initial investment of $2,000, and then I have E to the R. Now R is 8%, but we need to use that in decimal form, so we've got to do 0.08. You can't do just 8. And then the length of time we're interested in is 15 years. So that gives us approximately $6,640.23. So you can compare that to the amounts you get up in example 7. Now, the examples I've skipped over here in the notes are examples in the textbook, and I put by each one which example in the textbook it is so that you can find it. And then what I'm asking you to do is to watch the video that goes along with each of those examples in the textbook. And there's one more down here using a different formula called the logistic growth formula that models quantities whose growth is restricted in some way. So here's what a typical logistic growth graph will look like. It starts out looking exponential, and then it levels off because the growth is limited in some sense. So this dotted line here is the upper limit of the quantity. Since we're calling that f of t in this formula, I'll call it that. Why would growth be restricted in some way? Well, some examples of that situation would be population growth. So there's usually some sort of upper limit on a population based on, say, how much food can be produced. Or spread of rumors. As more and more people hear the rumor, there's fewer people to spread it to. So there's an upper limit to growth there. Anyway, please watch the videos for these examples. I'm hoping that you've already found where to watch the videos for the examples in the textbook. You can either go to, if you have your ebook, so if you purchased access to the ebook at xyztextbooks.com, then when you open the textbook, you'll notice next to the page on the right side will be videos that go along with the examples in the textbook. And there's several instructors, so you just pick the one that you like. If you didn't purchase the ebook, but you have a hard copy of the textbook, then there is a QR code next to each example. So you can use that to pull up the video to watch. And last, if you don't have either of these things, you can go to mathtv.com, search for the topic Applied Calculus, go to Chapter 4, scroll to 4.1, and you can watch the videos that go with the examples there. Okay, good luck with that. Let me know if you have any issues finding those or watching those.